Hello everyone, you're welcome to this channel once again. Today we have another question bordering the jet-propelled aircraft and how to calculate the minimum fuel required for its flight mission. Once again, we have a question on jet-propelled aircraft and how to calculate the minimum amount of fuel required for its flight. Now, let's read through the following question. Consider a jet-propelled airplane with the following parameters, with the wing area S 51 meters square and the wingspan 26 meter. The zero lift drag coefficient CDO equals 0.02. The Oxford efficiency factor E equals 0.85. The thrust specific fuel consumption TSFC equals 0.62 kilonewton per kilonewton hour. The operational MT plus pilot mass MOP equals 8,518 kg. The airplane has to deliver a payload of 887 kg by airdrop from the airport at the location A to location B. The distance between location A and B is 2,000 km. The mission consists of 3 phases. First, climb from airport at location A to 10,000 meter altitude, where the air density equals 0.41 kg per meter cube. 2. Cruise to location B. 3. Cruise at the same altitude back to location A. The payload is dropped by parachute at the location B from the altitude of 10,000 meters. Now, ignore the descent phase at the end of the mission. The fuel consumed during the climb phase is MFC 500 kg, and the distance covered during the climb phase is 100 km. The gravity acceleration is G equals 10 meter per second square. Now, calculate the minimum amount of fuel required for this mission in kilogram. Once again, calculate the minimum amount of fuel required for this mission. First of all, let's approach this question by pulling out all the flight parameters given to us. So therefore, today we have a jet propelled aircraft. With the jet propelled aircraft, we have the wing area S equals 51 meters squared. We have the span 26 meter. We have the CDO 0.02. We have the Oxford factor 0.85. We have the TSFC 0.62 kilonewton hour. We have the mass of operational, which is the mass of the pilot, and the heaviness of the aircraft, which is 8,418 kilogram. We have the mass of the payload, 887 kilogram. We have the distance from A to B, 2,000 kilometer. We have the altitude, 10,000 meter, which is above sea level. We have the density at 10,000 meter altitude, which is above sea level, which equals 0.41 kilogram meter cube. We have the mass consumed during the climb, mass of fuel consumed during the climb, which is 500 kilogram. We have the range attained during the climb, which is 1,000 kilometer, which is 100,000 meter. We have the G, acceleration due to gravity, 10 meter per second square. Now we are supposed to calculate the mass of the fuel for the whole flight. First of all, by using Breguet range equation, the R equals 1 over TSFC multiplied by HG over rho S multiplied by CL over CD to the root max multiplied by the root of initial mass to the final mass, the root of the final mass of the fuel. Now, by using this particular Breguet equation, we can deduce that the following factor here is constant. So by pulling out the constant, our constant, which is 1 over TSFC, becomes, let us forget, TSFC is in hour. To convert it to hour, it becomes 3,600 over 0.62 to the root of 8 multiplied by 10 over 0.41 times, what's the wing size? 51 multiplied by CLCD, So therefore, we need to calculate our CL and CD. To calculate our CL and CD by using CL equation, which is the root of pi over 3 EAR CDO. That becomes pi over 3 to the Oxford factor 0.85 times aspect ratio our aspect ratio equals p squared over x, which is 26 squared over 51. That gives us 13.26. So therefore, we have 13.26 multiplied by our CDO 0.02. So therefore, our CL becomes 0.49. Don't let us forget our CD equals 4 over 3 CDO. So therefore, it becomes 4 over 3 multiplied by 0.02. So therefore, our CD equals 0.027. Now, by inputting this value into this particular Bregret equation, now it becomes the root of 0.49 over 0.027. Therefore, our K equals 2.97 times 10 raised to the power 5. That's our K, which is a constant on the Bregret equation. Now that we have found K constant, the next thing is to start negotiating how to find the masses to apply. The range from B to A equals the K multiplied by the root at B minus the operational mass. Which is 2.97 times 10 raised to power 5. Into bracket the root of N B minus root of M O B. Now we can single out MB, our MB, that is the mass at B equals RPA over K constant plus MOP square MB becomes the range (2,000 km) over the K constant 2.97 times 10 raised to the power 5 plus the root of MOP, which is 8,518 kilogram square. That gives us 9,800 kilogram. So that's the mass when the aircraft reached the station B. Now, the range from A to B equals the rate of climb plus, that is the distance covered during the climb, plus K, which is a constant of Bragg equation, which equals the mass at A in the initial airport minus the mass at B plus the mass of the payload before it was dropped by the parachute. Now this becomes, to find our MA becomes the range of A to B over the K constant plus the root of MB plus M payload so therefore MA becomes, what's the range from A to B? 2 times 10 raised to the power 6 meter over K constant, which is 2.97 times 10 raised to the power 5 plus the root of, what's the mass at B? We have it now, 9,800 plus the mass of the payload, 887 square. So therefore our MA equals 12,060 kilogram. Now that we have the masses of the MOP, the masses at A, the masses of the payload, therefore, and we can deduce that the mass of air consumed the mass of fuel consumed equals mass at A minus the masses of operational minus the masses of payload minus the mass of fuel for the climb. So therefore, the mass of fuel consumed equals the mass at A, which equals 12,060 minus what's the operational mass minus 8,518 minus the mass of the payload minus 887 minus the mass of the fuel for the climb 500. So therefore, the mass of fuel for the whole mission of the flight equals 3,155 kilogram. Thank you for staying tuned.